Hey folks, welcome to this new series on JAX. In this series, we will just do a walkthrough of all the features of JAX, basically learn it from scratch. The eventual goal is that we should be able to read any JAX code, and I want to build up to us being able to read Llama implementations on JAX and even look at distributed implementations of JAX. So let's get started. Yeah, so what is JAX? I am not sure if you've heard about JAX or not, but it's becoming the next most popular library of deep learning after PyTorch. So PyTorch, made by Meta, and it is very tightly bound to CUDA. So every time someone has to write, every time someone comes up with new hardware implementations, or new accelerators, unraveling those PyTorch bindings from CUDA to whatever the new hardware is, if it's AWS Trainium, if it is AMD GPUs and so on, takes a lot of effort. So that's where a lot of people have started to move to JAX, because JAX is basically NumPy on steroids. And the whole idea of JAX is you just write it once. You don't worry about the deployment platform. You don't worry about the distributed nature. You don't worry about the hardware. You just write your code in pure NumPy-like fashion. And then JAX takes care of how to compile it, how to optimize it, how to distribute it, how to optimize it for the different hardware. That's the whole idea. So that's, some people call it JAX's NumPy on steroids with autograd. So autograd is you being able to take derivatives for free. So that's the benefit of JAX. And internally, JAX uses the XLA compiler made by Google, which used to be part of TensorFlow as well, to compile your programs, to JIT compile. So it does a just-in-time compilation. Now it also supports ahead of time, but the idea is that your code is optimized and compiled. That's the whole philosophy of JAX. And in addition, JAX is based on pure functions only. So if whatever I said made no sense, don't worry. We will get into all of that. But know that JAX is becoming the next big framework for deep learning. And it's good to know a little bit of JAX, at least being able to read JAX code. All the Google models, I believe, are now trained in JAX. And so Google is the big backer of JAX, and it's gaining a lot of popularity. So in this series, we will just go through bit by bit into JAX. And yeah, let's get started. So in this video, I'll just do arrays. Just arrays are the equivalent of tensors in PyTorch. So we will just look at how arrays behave in JAX. So first of all, again, JAX, let's see, what version is it? So it's still an early version. They're not at 1.0 yet, but it's quite stable. Unfortunately for me, I'm on a NVIDIA GPU, but I'm on a Windows machine. So as you can see, there is no support, but fortunately, I'm on WSL2, so I will still be able to use some JAX. During the later videos on JAX, when we actually do distributed training, I might switch to a Linux machine, but we'll see. So basically, I did this in WSL to install JAX with CUDA bindings, and yeah, and let's get started. So yeah, so here I have JAX loaded in. And I am on a notebook which is connected to my WSL machine. So for any JAX workflow, you want to import JAX, but there is also an interesting NumPy-like library called jax.numpy, which is virtually identical to NumPy. It's just that now you can use GPUs, now you can use devices instead of NumPy. So because NumPy is only CPU based, the jax.numpy library, which is, I believe, almost at feature parity, can just now optimize it for the different hardware and so on. So let's import all of this together, and just to check so I have just to so that I don't waste both of our times, I have the code over here in a notepad that I'll just copy paste sometimes. So I'll paste the notebook online somewhere in GitHub. It'll be in the description below. But yeah. So let's first see what version of JAX we're in. We're in 0.6.1, and we can also look at how many devices we have. So because I'm on a single device machine, so let me show you. So because I have like only one GPU, JAX tells me that you just have like if I had like 8 GPUs, if I was on a P4 or a P5 machine, then I would have a list of like 8 CUDA devices. The ID here refers to node. As far as I know, it's not process, but it's node. So if I had like multiple nodes, I would get ID 0 and ID 1 and so on. But or it might just be process. I'm not sure. We'll figure it out once we start working with TPUs. Right, so let's get started. So let's first create an array. And so here, just to make sure you can see, okay, so yeah, so here I have, I create an array just like you'll do for numpy of ones, an array full of like ones with shape 2, 3, and we print it, and then we'll do a shape. And again, and here I create an array that is just identity matrix, and we'll again do the shape. So I just want to like run it through you, run it and just show you. So just show you that how this jax.numpy is literally like numpy. Now let's just look at what is a type of these objects. Wait, did I mistype it? Okay, so you see that this is of type array. Almost everything in JAX would be an array. Like so earlier in JAX, things used to be device array, sharded array. So if you remember, or if you know, in Torch, there's tensors, there's D tensors, which are the distributed tensors, and there are like a bunch of other things. They're just like different abstractions. There's just one in this modern version of JAX array, and internally it takes care of sharding, internally it takes care of distributedness, but array implementation is the superclass that captures everything. And yeah, so that's and then you would pretty much do everything the same way you do you work with NumPy. So let's say if you wanted to create an array from a list, so in that case, so here I am creating from a list of lists. I create an array just like we do in NumPy. You can, so for example, and I can also convert a NumPy array into a regular array. So where I just like take in the NumPy array and I pass in, JAX numpy.array. A key thing to note is I believe most of the JAX functions require the array type. So you always want to do the conversion. You always want to convert your NumPy arrays into this JAX array format. I don't know if the operations will fail, but because they might be doing a silent conversion, but I know that they don't directly work on regular Python lists for sure. We'll take a look at those and see if just verify my claims. So now you've seen the parity between this JAX NumPy and regular NumPy. So okay, now let's try to do some indexing and slicing. So here I have pasted some code where I have an array 0 to 12 and I reshape it to 3 by 4, and we print it. So and then we basically like address the different elements, different lists, and so on the same way as we would do, or index into things the same way as we would do into NumPy. So again, okay, I've run into an error. Let's see what this is. Okay, so using a non-tuple sequence for multi-dimensional indexing is not allowed. So it's saying me I should use an array of sequence. So let's look at what is the offending. So here, when we're indexing array of 0 and 2, okay, we'll take a look at that. But first, let's look at what we have. So we were able to reshape our array. As you can see, it was printed. We could index the elements, which is fine. Index both according to row and column. We could call the first row and the first column, which is good. We could call the few sequence of elements, a subarray basically, which is also good. As you can see, we got the sequence. Now the issue was when we wanted to index the whole of row 0 and row 2. Now I believe the issue is because we are passing a list, and this list is so basically what we want the entire row 0 and entire row 2, but we're passing in a list, and I said Python lists don't work. So let's first try to convert this into a NumPy array and then see if this works. And it did. So okay, so note, because I just want row 0 and row 2, I will select the first two items and then the whole list. The first from the first indexing, I'll select 0 and 2 and then the whole thing. So that worked. I can also do JNP, which is the JAX array, and it still works. I wonder if I give it a list in the first dimension and a non-list in the second dimension, would it still work? Oh, okay. So the issue was we have a two-dimensional array and we were indexing it in a weird way. So I guess for indexing, lists still work. So you can just give it either a Python list, NumPy list, or a JAX list. So I guess that works. I was just a dummy in the way I wrote this whole thing, but that's good. And then you can do some kind of Boolean masking. So all of that stuff works pretty well. So this is good. So we've established that JAX is no different. Now let's try to do some basic operations. So let's first just do some matrix multiplication. Right? Matmul is a common thing that people do. So let's see if we can. So we create two arrays, and then what I will do is I will do matrix multiplication, and for this there is a function matmul which does a times b, and then we will output c. So we have a, we have b, the multiplication happened. Let me just double check if this makes sense. 5 plus 14 is 19, so that's good. Okay, so straightforward. What I want to do is I want to just also test if this will work with a list of lists, and my guess is that it won't. Let's just try it out. So clearly this failed because it expects either a NumPy array, or a JAX array or a scalar, but not a list. So NumPy arrays work, but regular lists won't. So let me just get rid of this. So that's the issue. So you want to ideally avoid using Python lists at all in JAX. Always use either NumPy or JAX arrays. This there are a lot of things that'll just work out of the box, like broadcasting and all that stuff. So I won't talk about that. Array transformations, when you're reshaping things, resizing things, will work the same way. But there is something that I want to show you about how the how do I say it? How the pure functional nature of checks is represented. So here, here on, I think NumPy also behaves the same way. So it's not an exact comparison, but let's just take a look. So first of all, I create an array, and then I reshape it. So what I will do, I'll reshape it, and I will also print back the original array. So when I do that, so whenever we look at this left-hand side equals to the original array and we are reshaping it, so any JAX operation returns a new object. So in NumPy, oh wow, that's why I hate AI, because it just doesn't turn off. In NumPy, the reshape function always returns a new object. So that's why this wouldn't be alarming. But all JAX functions, anything that you do in JAX, always returns a new object. It never alters the old one. Any function that you write out of it, any composite objects or functions that you built in JAX, need to have the same behavior. So your functions cannot have a state, and they need to be pure. That means they, for a given input, they will always produce the same output. And so you always have to create new objects or new variables where you store the output. The input is unaltered. But yeah, I get it. This is a bad example, but we'll see more complicated examples. Maybe another example, another way I can show you that is with the mutation ability. So let's create an array. So I have like this 1, 2, 3, 4. Now, what I want to do is I want to update a particular element. So if I do JAX array of 2, so that's 3, and I pass in, I get an error because JAX arrays are always immutable and do not support in-place assignment. So that is any time, because this is all like pure functions, the set thing needs to create. So whenever we set something at this value, it needs to create a new object, and that's why this in-place assignment doesn't work. So the way you would do this in JAX is you do this. So you call this .add function, and you pass in the index, and then what you want to set it as. Note that this okay, and it returns a new list. It's all a new array. So that's my new array, and we will print both the new one and the old one. So at the 0th position in the new one we have 99, and at the old one we have 1, 2, 3, 4. So that's the weird thing with JAX. So, and the set thing, you don't need to just pass in one index. You can pass in like multiple indices. You can do the indexing the same way as you do in any other case. You can set multiple things as well. So you're not restricted to just scalars. You can pass in lists, you can pass in arrays, you can pass in whatever. So one would think that, oh wow, because of this, because I can't do in-place assignment, I am creating new instances every time, new objects every time. That means I'm wasting memory. But that's where the optimization comes in. You write it in this way, and the compiler takes care of all the optimization. The compiler will do the optimization. You don't need to worry about it. So what's the bottom line? Arrays are immutable in JAX. Okay, so that's about arrays. I'm wondering if I want to talk about random numbers because they work in a different way. So let me just give a brief primer, and then we'll move on. I want to have separate videos about random numbers. So, like how let's first look at like how the random numbers in NumPy behave, and then we will look into like how they behave in JAX. So in NumPy, there is a global state associated to the random number generator, and your functions tend to update that state. However, because JAX is stateless, there is nothing to update, and you pass in the state as a variable, and that's why you have more control over the randomness. So let me just show you like what I mean is, so okay, what's this? Let me okay, so let's say I have this let me just generate like one random number. So first I set a seed. I mean, if I'm not setting a seed, it's by default something. So I get a random number, right? And let's say I was generating two random numbers, one after the other, and I set the seed every time. So in that case, I get the same numbers, 0.3, 0.3. What if I wasn't setting the seed? In that case, I get a different number, because right after this was called, this np.random goes and updates the seed. So let me find out like how do you actually so I'm trying to like look at like how can I retrieve the seed value, and it's telling me I cannot. Okay, what if I do this? Let me do a. Are there any? Is it? Let's see if. Oh, it's not. But it's okay. Maybe there's a way. I don't know, but I don't want to get bogged down. But the point is, this random goes and updates the seed. So that's why the next call gives me a different number. Now, in contrast, in JAX, you kind of get that for free. So let's see. Let me import the. So I first generate a key. So using a seed, you generate what's called a key. So let's first look at what the key is. I don't know, some random number. So right. So every time I give it this seed, it'll generate some. So just to show you, it generates a key, and now we will pass in that key to my random number generators. So it'll look like this. So I pass in a key, and I generate a value. So let's say if I'm generating two set of values, because I will pass the key explicitly, so I explicitly work with the state, I can control the determinism or randomness. Now this is both good and bad because you have to explicitly do the key management, but here you have more control because here it was just behind the scenes changing the seed value, and here you're explicitly controlling it. And this is because this maintains the functional nature of JAX, and because it has to be pure function, there cannot be any states, right? And so you might ask, okay, so do I need to do this every time? Not really. There are functions that will generate subkeys. You can split a key into subkeys, like this is a deterministic trajectory, and starting from a random variable, and you can use that. We will see examples of that, but this is how random numbers are handled in JAX, and that's the extent I want to get into of all of that. Okay, so we've talked about these arrays, But let's also talk about where the arrays are kept. So devices, right? So let's create a JAX array, and then I want to look at what device is it. So by default, JAX, this is the behavior of JAX. It'll pick whichever device it wants to use, and it knows, CUDA better than CPU. So my variables are kept in that particular device. So my array is on CUDA device. So this is equivalent to in PyTorch when you do the .2 to tensors. If I want to move it to CPU, what I can do is I can take my array and I can just do a dot device put, and I'll put it in CPU. So now if we do CPU dot device, CPU array dot device, you will see, sorry, it's CPU. Again, like I said, everything is functional. So here you pass in the array and you get a new one in return. So now you still have the original one in CUDA and the new one in on CPU. So that's just how JAX works. We've already covered the JAX.devices just to show you your list of devices. CPU is always there, and let me see if what this does do. Okay, so this is queries the number of CPU devices and number of GPU ones. So same thing. This will give me an error, but I just want to see it. Okay, we don't have TPU, so that's fine. Okay, so that's that. Finally, the thing that I want to show you is, because okay, let me first actually show you, and then we will dissect it. So first I create a very large array, and then I will compute the square of it. So and I want to time that operation. So note, I multiply it by itself and I time the operation. In the next call, I will multiply and I will call this block until ready function, and then I will compute the time. So let's run it. Note, again, let's run it again. There was a difference. I will talk about the difference as well. So first of all, every time I run it, you will see that when I do it without this blocking function, I get some insanely small amount of time. But with blocking, I get some realistic time. So what happens is, JAX, as soon as we call an operation, dispatches the operation. It doesn't care if it's done or not. Because it's in CUDA, it'll dispatch it asynchronously. Who cares? And it'll move on to the next line to process. So that's why so this is analogous to CUDA synchronization when you have like multi GPUs, or even in threads you want to synchronize. So that's why the time is super low, because the operation wasn't even done when we computed the time. The block until ready is, it waits for the operation to be complete, for the operation to yield back, and that is the realistic time. So that's why every time you want to just measure time, you want to, or synchronize things, you just call the block until ready. Now, what I don't know is, because this large array is a GPU device, would the behavior change if it was a CPU device? So let's do that again by creating a CPU version. So we'll just put it on CPU, and then we see, and looks like the behavior is the same. It will always just dispatch it so now you can see it will always just dispatch dispatch it asynchronously. So not a lot we can do. So okay, so the behavior is consistent among CPU and GPU. Okay, so that's what I want to talk about block until ready. The last thing is, if you just it was there only for only a half a second, but the first time this ran, there was a large amount of time that the without took. So let's see if I can reproduce this. Let me restart my notebook session. Let's load JAX, and I'll just load this. I'll get rid of the I mean, I can do it on the CPU as well. So let's run it. Okay, not a lot of difference. I don't know why the first time it took. Okay, right. So here, the first time I ran it on CUDA, there was a lot of time for this time without blocking. There are two reasons why I can imagine this is happening. So now when I run it the next time, it'll be pretty quick. The two reasons why is because so all operations in JAX are JIT compiled, and the first time an operation is run, it always takes longer because it's tracing and doing a compilation. We'll do a video on that. So it could be that, or yeah, I think it has to be that. So because the first operation is taking so long because it's being compiled. Okay, I kind of just realized like I got it all backwards. Let me try again. Okay, so let's go through the explanation again, and forgive me, I just realized I misspoke. I was talking about the asynchronous dispatching, how Torch does it. I was just looking at the JAX manual. So JAX has lazy execution, and it won't execute things till they're actually needed. So that is why the first operation is so quick, because when we write it down, it doesn't do anything till so here it hasn't done anything in the first execution because we haven't queried the result. So let me show you. If I do a print result 1, okay, so what I'll do is I'll do a print, and then if I do a print, you will see that time without blocking is more because there's a bottleneck of the print. So again, so this is more because when we do print, it has to materialize the array. That's why when we don't do a print, if I just did, I don't know, result 2 equals result 1 plus 1, even in this case, it doesn't have to materialize the array, and that's why the time is so less. Now, the first time the operation took time because every time we do a JAX operation, it does a compilation step. So here the computation graph is multiply and then add. So it does optimizations on that graph, and that's why the first run is always like more expensive, which is so that's the reason. What I was thinking is maybe it's like spending time and like making memory on the GPU device, but no, it's just optimization. So that's the reason. So here now the runs are like much quicker because in the lazy JAX execution, it's not doing anything. Here, when you do block until ready, it actually forces it to materialize, and that's the reason. So sorry, I went down. I don't know. It's late here. I went down a different chain of thought. So apologies. But yeah, so that's pretty much all I want to talk about JAX in the first video. There was a lot of rambling. I promise next time I'll do a better job. And all right, I'll see you in the next time. Cheers.